Okay, how many of you have finished the extra credit homework? How many of you have watched the videos? How many of you didn't watch the videos but still finished the homework? Okay, did you see partial fraction decomposition before in high school? Okay. What I'm going to do is that I wasn't going to talk about partial fraction decomposition in the class at all, but then in my morning class there were a lot of people who didn't really watch the videos. So then I decided to at least go over the big ideas of this section. I am not going to show you the details of the problems. They are left to the videos. If you need to know some of the details in my lecture today, I refer you to the videos, okay? They do a pretty good job on describing how to solve those problems. But I'm going to go over the main ideas and big ideas of the section. Partial fraction decomposition, and this is a technique for us. This technique is helpful to evaluate integrals involving rational functions. So, first of all, suppose that, first of all, there is one concept that I want to clear out. If you have a quadratic polynomial, a quadratic polynomial is called irreducible. When? A quadratic polynomial is irreducible when the corresponding quadratic equation has no real solution. Okay? Quadratic polynomial is irreducible when the corresponding quadratic equation has no real solution. So what does it mean? I know the quadratic formula. So if I have this quadratic equation, then the quadratic formula tells me x is minus b plus or minus root of b squared minus 4ac over 2a, and that solution will be complex when the quantity inside the root is what? Negative. The quantity inside the root is known as the discriminant of that quadratic. And so a quadratic polynomial is irreducible when the discriminant b squared minus 4ac is negative. Is everybody clear? Let's look at some examples of irreducible quadratics. I should say irreducible over the real numbers. Irreducible quadratic means that you cannot factor it into linear factors with real coefficients. However, you can, of course, factor out this quadratic into linear factors with complex numbers. Okay? So I should say irreducible over the reals. You cannot factor it into linear functions with real coefficients. Okay? In any case, that's how you know that a quadratic is irreducible. You need to be able to recognize that when you do the problems. Some examples of irreducible quadratics. X squared plus 4, is that irreducible? The easiest way to see that is simply notice the following. If I look at x squared plus 4 equals to 0, right? Does that equation have a real solution? Well, right away you see that x squared is what? Negative 4, and it tells you that this equation has no real solution, right? The left-hand side is non-negative, the right-hand side is negative, right? So you know that x squared plus 4 is non-negative. Irreducible. The second one is I'm going to look at the corresponding quadratic equation, and then I'm going to solve for x, and it's going to give me what? Negative 1 plus or minus 1 squared minus 4 times 1 times 1 divided by 2 times 1. And is it clear that the discriminant is negative? So both solutions here are complex solutions. So x squared plus x plus 1 is irreducible as well. How about the third one? Well, look at 4x squared minus 4x plus 3. Is that irreducible? Well, solve for x. You're going to get negative 4 plus or minus negative 4 squared minus 4 times 4 times 3, is it correct? Divided by 2 times what? I don't even have to look at the denominator. I mean, I look at the main thing you want to look at is the quantity inside the root, and that's the negative quantity, right? Is everybody clear? The first one is 4 squared, which is 16, minus 4 times 4, which is already 16 times 3. So that's negative. So this discriminant is negative, being that tells you that the polynomial, the quadratic, is an irreducible quadratic. Is everybody clear why these are irreducible? All right. Let's, for a few seconds, talk about some baby math. P over Q. A rational function P over Q is a fraction. When is a fraction proper and when is a fraction improper? The fraction 1 over 2, 1 divided by 2, is that proper or improper? Proper means numerator is smaller than the denominator. Improper means numerator is bigger. So 3/2, that's improper. What is 2 divided by 2? Improper. I want the numerator strictly less than the denominator. Now, for rational functions, P over Q, it is proper when the degree of the numerator is strictly less than the degree of the denominator. Okay? Now, a rational function is improper when the degree of the numerator is bigger or equal to the degree of the denominator. So let me just give you some examples here. Proper versus improper. So if I have the rational function x over x plus 1, is that proper or improper? Improper. The degree of the numerator is the same as the degree of the denominator. So this is improper. Now if I have x squared minus 2 over x cubed plus 3x plus 2, that's a proper fraction. Again, proper means degree of the numerator is strictly less than the degree of the denominator. Improper means degree of the numerator is bigger or equal to the degree of the denominator. Am I okay? All right. So that's what it means to say proper or improper fraction. Now, before you apply partial fraction decomposition, you have to make sure you have a proper fraction. Okay? Don't apply partial fraction decomposition to an improper fraction. Okay, so let's suppose that P divided by Q is a proper fraction. I'm starting with a proper fraction, P over Q, meaning that degree of P is less than degree of Q. Okay? Degree of P less than the degree of Q. That's proper. Now, the first step to write down the decomposition is that you're going to factor out the denominator. So when you factor out the denominator Q, always you're going to end up with bunch of linear factors and bunch of irreducible quadratic factors. When you factor out the denominator, right, each factor will either be a linear factor to some power, or it will be an irreducible quadratic to some power. Am I making sense? So let's say that your factorization of the denominator looks like this. Don't worry about the notation here too much. All I'm saying, there are r there are R linear factors, and there are K quadratic factors, irreducible quadratic factors. And each linear factor may come with some multiplicity. So whatever the exponent is on the linear factor, it's called the multiplicity of that factor. Am I making sense? N1 is the multiplicity of the first factor. NR is the multiplicity of the rth linear factor. Same way, M1 is the multiplicity of the quadratic factor a1x squared plus b1x plus c1. Is everybody clear? Now, once I have the factorization of Q into linear and quadratic factors with certain multiplicities, I want to write down the partial fraction decomposition. So what's the partial fraction decomposition? Each factor of Q, the denominator, each factor of the denominator will contribute a term in the decomposition. Each factor of Q will contribute a term in the decomposition. Now let's think about one factor of the Q. Let's say dix plus ei to the power ni. That's the linear factor with multiplicity ni. I'm just saying one of them. Di, ei, they are fixed number like 2 and 2, 1, things like that. So what would be the contribution of this factor in the decomposition? Here is the contribution of just this linear factor. In the decomposition for the linear factor dix plus ei to the ni, for that linear factor, the contribution you're going to get in the decomposition is the following. You are going to get ni different fractions, ni fractions. In each one of them, the denominator will be a power of the linear factor. So you're going to start with the first power of the linear factor, the second power of linear factor, all the way up to the ni power of the linear factor. And then, so those powers will go into in the denominators, and each numerator will be a constant. Am I clear? So each linear factor of Q will give rise to a term like this in the decomposition. I'm going to explain that in examples in a bit. So once again, I have a linear factor with multiplicity ni. What is the contribution of that factor in the decomposition? In the decomposition, I'm going to get ni fraction. The denominator of the first fraction would be the same linear factor to the power 1. The denominator of the second term will be the linear factor to the power 2, so on, until you get the power ni. And each numerator is just a constant. Same thing happens for a quad. So why am I saying summation? Well, I'm saying this would be whatever I have inside the brackets, that's the contribution of one factor. So I am summing over all the factors, all the linear factors. And then the quadratic factors, if you have, let's say I have a quadratic factor aix squared bix plus ci to the mi. So mi is the multiplicity. I get the same thing. I'm going to get mi fractions. The first fraction will have denominator same as the quadratic factor with exponent 1. The second fraction will have denominator the same quadratic with exponent 2, and so on until you get exponent mi, the multiplicity mi. And then what are the numerators? Each numerator is a linear function. Each numerator will be a linear function. So when you have a quadratic denominator, the numerator is linear. When you have a linear denominator, the numerator is constant. The degree is always 1 less. Okay? If that makes sense, let's go over some examples. It's going to make it more clear. Now, this way of writing, the right-hand side that I have, that's called the partial fraction decomposition of P over Q. The partial fraction decomposition of P over Q means that you can write it as a sum of simpler fractions where each fraction is either a constant over a power of a linear factor, or it's a linear function divided by a power of a quadratic factor. That's what it means. Each term on the right hand side is either a constant over a power of a linear factor or a linear function over a power of a quadratic factor. And that's the partial fraction decomposition. And this is also used in differential equations. Here we have only one section on it, but in DPQ you're going to have one entire chapter where you have to use that. Now, and by the way, I don't think your instructor is going to bother to go over the details of this decomposition. So you have to know it from here. Now, let's start with this. Why don't you guys close your eyes? And when I delete everything that I have there, okay? Close your eyes, don't cheat. Was I fast enough? Did you guys see that? I tried my best. Okay. We want to write down the partial fraction decomposition. I want to write down the partial fraction decomposition for this. If you can write down the partial fraction decomposition for this example, you have arrived. You know what to do. Okay? Because I have all the different mixtures you can have. You can have a linear factor power. You can have a quadratic factor power, right? So if you can write down the partial fraction decomposition for this one, then you can write down the partial fraction decomposition for any given fraction. Okay, so let's write it down. The denominator is already factored out. Now, x squared. Is x squared a quadratic factor, or is it a linear factor with multiplicity 2? Well, it's got to be a linear factor multiplicity 2 because x times x, right? X squared is not a irreducible quadratic. It is reducible. You can write x squared as x times x. So x squared is a linear factor with exponent 2. What will be the contribution of that to the decomposition? Let's write that down. What's the contribution of x squared? Now, x squared, because the multiplicity is 2, is going to contribute how many terms? It's going to contribute 2 terms. One with the denominator just x. The another one will have denominator x squared. Now, what's going to go on top? Some constants. Let's say a and b. Hopefully we're not going to need more than 26 letters, right? Okay. Plus, what will be the contribution of 1 minus x? It will be 1 minus x in the denominator and c over there. That's the easy one. What would be the contribution of 2x plus 3 cubed? How many terms will it contribute? 3 of them. Let me write 3 of them. Okay, the first one will have the linear factor with exponent 1, then the second one with exponent 2, and the third one with exponent 3. And then in the numerator I'm going to get D, E, and F. Okay, what's the contribution of the... Notice that I have 4 plus x squared, right? Is that irreducible? 4 plus x squared will be irreducible, right? Clear, because you can never get a real solution, real root of this polynomial, right? This polynomial is never 0, for example, right? Am I okay? So, in terms of graph, what's the meaning of an irreducible quadratic? In terms of the graph, what's the graph of a quadratic? parabola. In terms of the graph, what's the meaning of irreducible? Doesn't have any x-intercepts. Very good. So now, what's the contribution of 4 plus x squared to the 3? I'm going to get 3 of them, right? There are 3 fractions which will be contributed by that. One of them will have denominator 4 plus x squared. The second one will have 4 plus x squared squared. Third one would be 4 plus x squared to the 3. And what's going to go on the numerators? Linear, right? So I'm going to get gx h. And then I'm going to have ix plus j, and then kx plus L plus the last quadratic is also a irreducible quadratic, but it has multiplicity 1, so I'm going to get only one. There will be only one fraction contributed by that in the decomposition, and in the numerator I'm again going to have a linear mx plus n. Is everybody okay? Okay, your homework is to solve for a, b, c all the way up to n. Okay? Good luck with it. No, I'm kidding. Although I remember when I was a student, my mean teacher actually made me do this, but I'm not going to make you do this. But that's not the. When we have a problem like this, we are going to just let the computer do it. However, it's important to understand. It's important to understand how to write down the partial fraction decomposition, the form, without solving for the constants. It's also important to know how to solve for the constants when you have simple problems. And I'm going to show you some examples of that in a bit. So what problems, for what type of decompositions will I expect you to know how to solve for ABCDs? Okay? And I'm going to show you some examples in a second. For something like this, I want you to know how to write down the decomposition. I'm not going to make you solve for the constants unless I give you a lot of time in the exam to do it. Is everybody clear? Okay, so let's just say that in the exam maybe there shouldn't be more than D. There shouldn't be more than D or E in the exam. Okay. Usually in the exam what I do is that I give you a problem where I ask you to write down the decomposition, something like this, where I want you to write down the decomposition, and then I give you a second part where I give you a simpler problem where you have to find A, B, C, and D. Okay? And again, I'm going to show you some examples in a second. Okay, what is decomposition good for? Well, for us, it's about evaluating integrals. So let's look at one problem. Again, in these problems, I'm not going to show you the details. Some of the details are left to the videos. Okay. What's the integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x? How would I find that integral? Well, I'm going to use decomposition. Rewrite the fraction as in terms of its decomposition, and then we're going to integrate. What's the first step? The first step is that I have to factor out the denominator. If I factor out the denominator, in this case, I am very happy to see that all factors are linear. When you have all factors are linear with multiplicity 1, that's the simplest possible case. Now, how do I factor them out? Those of you who have taken Calc1 with me, we went through a painful process where I assigned 80 or 90 problems, or even more than that in WebAssign, and also you did a lot of exercises where you reviewed algebra, and some of the problems were about factoring, right? Hopefully you still remember them. How would you factor this out? What's the first thing you're going to do? take out x, and then you're going to get a quadratic, and you know how to factor out a quadratic. So if you do that, you're going to get x, 2x minus 1, x plus 2. Again, I'm not going to show you the details today, but if you should make sure you know how to fill in the gaps. If you can't, you should come by my office. I'm going to show you how to do that. All right, so this is the integral. Now I'm going to write down the partial fraction decomposition. Even before I started doing this, I have to make sure my fraction is proper. Is it proper? Yes, because the degree of the denominator is bigger than the degree of the numerator. So you have to make sure it's proper. Okay, once I have this, then I can write down the partial fraction decomposition. What would be the contribution of x? A over x. What's the contribution of 2x minus 1? B over 2x minus 1. Contribution of x plus 2. C over x plus 2. What's the next step? The next step is that I have to find A, B, and C. Today, I'm just going to say what they are. A, B, and C will be half, 1/5, and negative 1/10. How did I get them? I'm not showing you the details here. Look at the videos, and otherwise you can come by my office and ask me how to get there. Okay. Maybe one day I'm going to do one big example where I'm going to show you how to find A, B, C's and all that. Okay? But today we're going to concentrate only on the big idea. So once I have the partial fraction decomposition written, I'm going to solve for the constants A, B, C, and then I'm going to write down what I have. And then notice that the first, I'm going to half over x, that's the same as half integral of 1 over x. This would be 1/5 integral of 1 over 2x minus 1. This would be negative 1/10 integral of 1 over x plus 2. Are you guys okay with that simplification? You guys are okay with that? Now, what's the integral of 1 over x? What's the integral of 1 over x? ln of absolute value of x. What's the integral of what's the integral here? It's going to be ln of x plus 2, right? ln of absolute value of x plus 2. I'm going to show you a little bit in detail what's the integral in the middle. The integral in the middle is 1 over 2x minus 1 dx. I have a 1/5 outside, but what should you do to find this integral? You should be taking u to be what? 2x minus 1. And if you take u to be 2x minus 1, what will be du? It will be 2 times dx, right? You agree? So if you do the substitution, what are you going to get? 1 over u, and then what is dx? Half du, right? Half du. And then if you carry this out, you get half integral of 1 over u, and then you get half ln of absolute u, and then finally, what is u? U was 2x minus 1, right? And that's how I got this. Remember, I had a 1/5 outside before. I have another half. 1/2 and 1/5 is giving me that 1/10. Is everybody clear? So that's how I got that integral ln of absolute value of 2x minus 1. If you can do that in your head and write down the final answer, that will be fine. Is everybody clear? How to get those integrals? In fact, these are the easiest integrals that you can obtain in this type of problems. We'll see more where the integrals might be a little bit more involved. the worst case happens when does the worst case happen? The worst case happens when you have a quadratic factor, and when you have a quadratic factor, then you have to complete the square and then do some other stuff with it. We'll see some examples in a second. Any questions on this example? Any questions at all? No? Okay, let's look at the next example. The next example that I have is the integral of x to the 4 negative 2x squared plus 4x plus 1 divided by x cubed minus x squared minus x plus 1. Okay, what's the first thing you want to ask? Is it proper or is it improper? Well, in this case, it's improper. The degree of the numerator is 1 bigger than the degree of the denominator. So, what's the first step? I have to rewrite it in terms of a proper, right? A polynomial plus a proper. How would I do it? By using long division. So whatever, you have to search through your childhood memory, right? Go to when you learn long division. Do you want me to do the long division? Should I do it? You can do it? Everybody feels okay with the long division? Okay, so then if you use long division, you're going to come up with the quotient, right? That quotient is x plus 1, and you're going to get a remainder, and the remainder is 4x. So the quotient plus the remainder over the divisor, right? So use the long division, come up with the quotient and remainder, and rewrite your fraction in this way. Once I have this, we already know how to integrate x plus 1, right? Yeah, that's just the integral of a polynomial. We know what to do by using the power rule. So now we concentrate on the integral of 4x over x cubed minus x squared minus x plus 1. That's a proper fraction. We can use partial fraction decomposition on it. Now, x cubed minus x squared plus minus x plus 1. How would you factor that out? What's the trick? What's the trick to factor out a cube? I'm sorry? Yeah, in this case you can just do it by grouping. You're going to group together the first two. You're going to group together the second two terms. From the second two terms, what are you going to factor out? Negative 1. From the first two terms, factor out x squared. So if you factor out x squared, you're going to get x minus 1, right? Let me write it in red. So you're going to get x squared times x minus 1, and here you're going to factor out negative 1, you're going to get x minus 1. And once you do that, now x minus 1 is a common factor. You can factor that out. And if you factor out x minus 1, what do you end up with? So you're going to get x minus 1 factored out. You're going to get x squared minus 1. And then what is x squared minus 1? X minus 1, x plus 1, right? So factor out x squared minus 1, and then you're going to get x minus 1 squared times x plus 1. Okay? So that's how you can factor that out. Let me erase that. Once I factor it out, then I get this. Now what's the partial fraction decomposition? Well, for the factor x minus 1, the multiplicity is 2 because the exponent on x minus 1 is 2. So I'm going to get two fractions in the decomposition for that factor. One of them would be a over x minus 1, the other one would be b over x minus 1 squared. The other linear factor is x plus 1, and the contribution of that factor to the decomposition would be just c over x plus 1. One term only because the multiplicity is 1. Everybody's clear? And once I have written down the decomposition, I have to solve for A, B, C. I'm not going to show you the details on that. Let me just say that A is 1, B is 2, C is -1. Once I know that, now I'm going to take the integral of 1 over x minus 1, integral of 2 over x minus 1 squared, integral of 1 over x plus 1. What's the integral of 1 over x minus 1? That's log of absolute x minus 1. What's the integral of 1 over x plus 1? That's log of absolute x plus 1. And what's the integral of 2 over x minus 1 squared? Let me show you that here. What's the integral of 2 over x minus 1 squared? What do I need to do here? You take u to be what? X minus 1, right? So if you take u to be x minus 1, what do you get? Integral of what? 2 over u squared du, right? That's going to be the same as 2 integral of u to the -2 du, right? What is that? 2. What's the integral of u to the -2? Negative u to the -2, -1, right? -1, which would be then -2 over u, right? Is that correct? And then finally, u is x minus 1. So I'm going to end up with -2 over x minus 1. That's what I have. Is everybody okay? Any questions on that? So only thing that's missing in my discussion is the details about how I solve for A, B, and C, right? All right. Are you done writing it down? Let's go to the next example. Here we have the integral of 2x squared minus x plus 4 over x cubed plus 4x. In this case, it is a proper fraction. So in the denominator, I can factor it out very easily. X times x squared plus 4. X squared plus 4, is that a irreducible polynomial? Yes. So then I can write down the partial fraction decomposition for the linear factor x with multiplicity 1. I'm going to get only one fraction in the decomposition. That will be a over x. For the quadratic factor x squared plus 4 with multiplicity 1 again, I'm going to get only one fraction in the decomposition, and that's going to be bx plus c over x squared plus 4. Now I have to solve for a, b, and c, right? For something like this, I definitely want you to know how to solve for a, b, and c. It's pretty easy to do. Again, I'm going to show you the details maybe another time, but these are in the videos as well. What is a here? A is 1, b is 1, and c is -1. So you're going to end up with 1 over x plus x minus 1 over x squared plus 4. The question is, I know how to find the integral of 1 over x, and I need to know how to find the integral of x minus 1 over x squared plus 4. When you have that, you need to check, first of all, look at the derivative of the denominator. Is it in the numerator? And the answer is no, not quite. So what I'm going to do is I'm going to break this fraction into two. One of them will be x. Let me know if you still need time to write it down. How many of you are done with the first row there? Okay. So let me hide that. Now, I'm going to break it into two terms. One would be x over x squared plus 4. The other one would be negative 1. The other one would be negative, and then integral of 1 over x squared plus 4, right? You agree? So write the fraction x minus 1 over x squared plus 4 into 2, which would be x over x squared plus 4 and 1 over minus 1 over x squared plus 4. Now, what's the integral? What are the integrals? Yeah, so if I look at the integral of x over x squared plus 4, notice the derivative of the denominator is 2x, which is almost in the numerator. So that tells you take u to be x squared plus 4. So if I do that, what would be du? Du would be 2x dx. In other words, x dx would be what? What will be x dx? Half du, right? Half du would be x dx. So here I'm going to get 1 over u half du, right? So x and dx together becomes half du, and x squared plus 4 is u. So then I can write it as half integral of 1 over u du, and that's going to be half ln of absolute u. And finally, what is u? Finally, u is ln, u is x squared plus 4. I am not writing a absolute value anymore because x squared plus 4 is already positive. So that's what I get for the middle integral, half ln of x squared plus 4. What's the integral of 1 over x squared plus 4? Well, if the 4 was a 1, right? If this was a 1, then I know it's tangent inverse, right? So that tells me this has to do with the tangent inverse. And if you are smart enough, you're going to write that formula for tangent inverse in your cheat sheet. And what's the integral of 1 over a squared plus x squared? So yeah, 1 over a times tangent inverse of x over a. So that's exactly half tangent inverse of x over 2 plus c. Is everybody okay? So you're going to have to use that. Use the formula for what? 1 over a squared plus x squared dx. If you don't remember that, you have to substitute x with au and then do a substitution, make it look like 1 over 1 plus u squared, and 1 over 1 plus u squared, you have to remember, is the derivative of tangent inverse of u. Okay? In any way, at the end you get that expression. Any questions? No? Finding the integrals making sense? Okay, again, the details that I left out here is finding a, b, and c. 5 minutes, so I could probably try to do one more. You guys have written that down? Okay, last one. What's the integral of 4x squared minus 4x plus 2 divided by 4x squared minus 4x plus 3? It's an improper, right? Same degrees, right? So I have to use long division only once. It's going to be very quick. So when you do long division, you're going to get a quotient of 1, remainder of x minus 1. So you can rewrite your fraction as 1 plus x minus 1 over 4x squared minus 4x plus 3. Okay? This is where the problem is. The denominator. So I already have the partial fraction decomposition. I don't have to do anything. Why? Because if you look at the proper fraction, the denominator is already an irreducible polynomial, and the numerator is a linear factor, so this is already in decomposition form. I don't have to do decomposition here. So x minus 1 over the irreducible quadratic. What should I do here? Looking at it, I have no clue. Since I have no clue, what I'm going to do is complete the square in the denominator. So I completed the square in the denominator. I showed you how to do that before. And if you do that, you're going to get 2 plus 2x minus 1 squared. Once you have that, you're going to do a substitution. And the substitution you're going to do is you're going to take u to be 2x minus 1. Okay, so do that. If you take u to be 2x minus 1, what is x? If you take u to be 2x minus 1, x would be u plus 1 over 2. That's the same as half of u plus half. So that tells you dx would be half du. Dx is half du. Now plug them in. You're going to get u plus x would be u plus 1 over 2 minus 1. And then 2 plus u squared. Dx is half du. Okay? You have to simplify this integrand. Notice that in the numerator you have u plus 1 over 2 minus 1, right? How would you simplify that? Isn't that the same as u plus 1 minus 2 over 2? So you're going to end up with what? U minus 1 over 2, right? So my point is, the numerator here is u minus 1 over 2. Okay? Now, what do you have then? You have u minus 1 over 2 divided by 2 plus u squared times a half. What is that equal to? Well, that's the same as u minus 1 over 2 times 2 plus u squared times a half. And then I get 1/4 u minus 1 over 2 plus u squared. Okay? It simplifies down to that. Is everybody okay? Now, once I have u minus 1 over that, I do the same thing as before. Break it into 2. U divided by 2 plus u squared. U divided by 2 plus u squared. Negative 1 over 2 plus u squared. I took the negative outside. Now, once I have that, then I do the same thing as before for the second integral. For the first integral. You're going to do another substitution here. What will be the substitution? Let's say take b to be the denominator. And if you do that, you're going to end up with ln of 2 plus u squared. ln of 2 plus u squared with a half. And then the second one, what will that be? Again, tangent inverse of what? Radical 2 now, because it's not 4, it's 2. So you get tangent inverse of u over root 2, and outside you're going to get 1 over root 2. At the end, though, you have to go back to x, and remember u was 2x minus 1. So u was 2x minus 1. You plug that in, and finally you end up with that. Okay? Did the steps make sense? Someday I'm going to show you at least one example where I solve A, B, C, and D, the constants. Okay? But again, look at the videos, you'll see how to do that.